Have you ever stopped to think about how we actually describe things like movement or force or even just giving directions? It turns out the universe has this hidden language it uses for all that stuff, and it's about way more than just numbers. Today, we're going to decode that language. We're talking about vectors. So, let's kick things off with a little thought experiment. Picture this. You're out camping and your friend comes running over, totally breathless, and says they found buried treasure just 6 kilometers away. Awesome, right? But here's the real question. Can you actually go and find it based on just that? Honestly, not a chance. You'd just be wandering around in circles. That number, 6 kilometers, it tells you the distance, sure, but it tells you absolutely nothing about where to go. Is it 6 kilometers that way, or up that hill? See, the number by itself is pretty much useless. And that simple little treasure hunt problem, well, it gets right to the heart of our first big idea. In the real world, whether you're trying to navigate a forest or, build a skyscraper, just having a number is only half the story. This is where we need to separate two really fundamental ideas. So on one side, you have what we call scalars. You can just think of these as simple numbers. They have a size, a magnitude, 50 minutes, 65 liters. They tell you how much. But on the other side, you've got vectors. And vectors give you the whole picture. They have a number and a direction. Not just 6 kilometers, but 6 kilometers northeast. That is a vector. And that is how you find the treasure. Okay, so if vectors are the key to everything, we probably ought to know what they look like and how they tick, right? So let's break one down and look at its basic anatomy. All right, so the official definition is that a vector is any quantity that has both a magnitude, a size, and a direction. And the simplest, most elegant way we draw this idea is just with an arrow. And this simple little arrow is just packed with information. Its tail is your starting point. The pointy end, the head, that's your destination. And the length of the arrow itself, that represents the magnitude. How far, how fast, how much force. And one key thing to remember, that magnitude, the length, is always a positive number. So one arrow represents one leg of a journey. Simple enough. But let's be real. Most journeys, most real-world problems, they're not that simple. What happens when you have a whole bunch of steps, all with different directions and different distances? How do you figure out where you end up? Well, the way we do it is actually incredibly visual and, believe it or not, really intuitive. When you want to add a bunch of vectors together, you basically just lay them out one after another. It's called the tail-to-head method, and it's literally like drawing out a map of your path. Let's walk through it. So you draw your first vector, say 5 kilometers north. Then, right at the arrowhead of that first one, you start drawing your second vector. Its tail goes right on the head of the first one. Let's say that's 3 kilometers west. You just keep doing that, chaining them together for every single step of the journey. And when you're all done, your final result, your total displacement, is just one new arrow drawn from the very beginning, the tail of the first vector, all the way to the head of the very last one. And that final vector, the one that shows the overall result of the whole trip, it has a special name. As the source material says, the vector sum of 2 or more vectors is called the resultant vector, or for short, the resultant. It's the one vector that sums up the entire path. But here is where it gets really, really cool. This method isn't just for drawing maps. This exact same idea is how physicists and engineers figure out what happens when you have a whole bunch of different forces all pushing and pulling on one object at the same time. So let's actually put that idea into practice with a fantastic example from the source material. An epic tug of war with some very, very strong dogs. Welcome to the main event. In this tug of war, we've got 3 contenders. First, we have Astro, pulling with a force of 160 newtons at an angle of 30 degrees south of east. Then there's Balto, pulling with 200 newtons. And finally, Clifford, with 140. Each one is a unique force factor, a specific strength in a specific direction. Now, here's the twist. The toy in the middle isn't moving. It's perfectly still. What does that tell us? It tells us something incredibly important. There must be a fourth dog, Doug, who's pulling with a force that is perfectly, exactly canceling out the combined pull of the other 3. His force vector is creating a perfect state of equilibrium. So how hard is Doug pulling? Well, to figure it out, we'd add up the force vectors for Astro, Balto, and Clifford using that same tail-to-head method. That would give us their combined resultant force. And since we know the toy is stable, we know that Doug's force has to be equal in strength and exactly opposite in direction. And when you do the math, that force comes out to a whopping 236.4 newtons. That is a precise answer you could never, ever get just by guessing. And that's the whole point, right? This isn't really about dogs. This is about engineering. By understanding how to add up force vectors, engineers can predict all the forces acting on a bridge, or a building, or an airplane wing. And they can design structures that are perfectly balanced and stable, making sure they stay put. Okay, let's quickly recap the big ideas. What should you remember? First, vectors have both a size, a magnitude, and a direction. Second, we draw them as simple arrows. Third, we can add them up visually, tail to head, to find the combined result. And finally, this simple concept is the language we use to describe forces, speed, and how things move. Because once you know what you're looking for, you start to realize that vectors are absolutely everywhere. They describe the speed of a planet in orbit, the pull of gravity holding you to the Earth, the push of the wind, even the invisible lines of a magnetic field. It is no exaggeration to say that the fundamental laws of our universe are written in this hidden language of vectors.